Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math basic course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into the Chapter 3 test in cumulative assessment in the Big Ideas Math Integrated Math 1 textbook. Now, this is the end of the chapter, so let this be your chapterly reminder of, as this one is called, test. This time it is the less teaching, more doing version of it, unless there's something I feel compelled I have to do, or unless I really struggle through a problem myself, which sometimes I do. Some of these questions can be kind of difficult. 16 questions in the Chapter 3 test portion. They'll be down below. Find the PDF in the description section separately from the cumulative assessment, and also each problem will be laid out by timestamp. And then the cumulative assessment, again, down below, and also graph paper as needed because we've been doing some graphs. I will choose which kind of graph thing I'm going to do. If they just said sketch a graph and there's a standard form equation, I'll probably do it out of standard form. If it's slope-intercept form, I'll probably do it out of that. So it just depends on what the question is. And as always, cumulative assessment can ask any questions out of chapters 1, 2, or 3. So equations, inequalities, and graphing linear functions. Without further ado, I'm going to go ahead and get started. We are going to start with numbers 1, 2, and 3, where you determine whether the relation is a function. If the relation is a function, determine whether it's linear or nonlinear. So this is two things in one, kind of interesting. So on question 1, we're first starting off with, is it a function? You know what? It is a function. The x's do not repeat in any sort of way, so each input has exactly one output. So it is a function? Absolutely. Let me copy and paste this table over, though, because I need to determine whether or not it's linear next. But is it a function? Yes. So this is a function. Every input has exactly one output. Now, is it linear? That's a different question entirely. As x's are increasing by a constant amount of 1, are the y's increasing or decreasing by a constant amount? Well, this is minus 1, and then plus 4, and then plus 5. I might have messed up some math somewhere. I don't think so, but those aren't constant. Is it linear? No. This is nonlinear. Nonlinear, as y changes by, so y does not change by a constant amount, as x does. So there's number 1. Number 2 is y equals negative 2x plus 3. I honestly don't have any work to show to answer these portions of this question next. There are so few equations that we're going to run into that make something a function or not. In this case, just simply because y exists in this thing, it's not a vertical line. And if it's not a vertical line, it's likely going to be a function. Now, there are equations of circles and things like that. This is nothing like that. This is slope-intercept form. This is a linear function right off the bat. I'm going to answer both. This is a linear function. Linear functions can be written in the form y equals mx plus b, and that's what this is. So you have this, you got linear, you got function, you got both of them. So that one's good, ready to go. Number 3, x equals negative 2. Here's a version of what I was stating that in equation form you couldn't have as a function. So it says if it's a function or not, this is not. This is x equals negative 2. This is a vertical line. Vertical lines fail their own vertical line test, which is having multiple y's for the same x. Not a function. Vertical line. Yeah, it is a vertical line. Now, if it's a vertical line, that means it's a linear equation, but it's not a linear function. We're not trying to state more about it. They said only if it's a function to determine the next part. So I'm good. Moving on. Numbers 4 through 6 say graph the linear equation and identify the intercepts. So here I have a choice of form I'd like to go to. And here I'm going to stick with standard form. When I look at numbers 5 and 6, they really seem to be out of that standard form-esque set of section 3.4 to me, all three of them. That doesn't mean that you can't take an equation like this one and put it in slope-intercept form. Do we graph? Let me see. Do we graph it as slope-intercept form later? You know, we slightly do later. Yeah, you know what? I think we do. Okay, I think we're good. So I'm going to go ahead and graph this one out of standard form, which means I'm going to find the x-intercept, y-intercept. They did say identify the intercepts. I think this is prime for this. Set y equal to 0. You have an equation that says 2x equals 6. When I divide both sides by 2, I get x equals 3. And for the y-intercept, I set x equal to 0. That means I get negative 3y equals 6 as an equation. And when x equals 0, y equals negative 2 when you divide both sides by negative 3. Now I'd like to graph this thing. Let me copy and paste this graph that I have here. And we're going to plot those two intercepts and draw a line through them. They did say identify the intercepts. We got them. So once we have this thing graphed, we're done. Use a straight edge to draw this line because we're going to complete it, not just right here. We're going to go as far out as we can on our own window range. So out here and out here. If you got this in slope-intercept form, your equation should say y equals 2/3 x minus 2. I can tell just based off the graph that we're looking at. And I think in our next chapter, we're going to have to do something like that. Write an equation based off a graph or other information. Number 5 says y equals 4.5. Now, as much as standard form can help us identify that we have a y-intercept indeed of 4.5, we have a y-intercept of 4.5. That doesn't tell us the rest of the graph necessarily. Let's look at what this graph looks like by maybe even talking about slope-intercept form a little bit here. Slope-intercept form is y equals mx plus b. I can rewrite this in y equals mx plus b by stating that the b is 4.5 and the mx, what makes x go away, is a slope of 0. Now, a slope of 0 is the graph of a horizontal line. Now, first of all, 4.5 is between 4 and 5, which is like this. But if I were to graph a horizontal line through this with a slope of 0, it would look like this. So this will be the equation of this line. Y equals equations are horizontal lines. Now, they said identify x and y intercepts. That's the y-intercept. There is no x-intercept here. A little bit of a trick question. It doesn't cross the x-axis. It's parallel to the x-axis. Therefore, there's no x-intercept. You know, it never said to state one way or the other, but don't state one if there isn't one. So I'm just stating none. It says intercept or intercepts, which is part of the tricky part. Number 6 is going to be a lot more of the same. We just saw what an example of an x equals equation is going to look like. It's going to be a vertical line. So if a y equals equation is a horizontal line and x equals equation is a vertical line, x equals 10 means this is your x-intercept at 10. And a vertical line means it'll never hit the y-axis. So this time, we're just going to go up and down from 10. No y-intercept. This is your graph. Undefined slope. Not a function. It's linear, but not a function. So y-intercept's none. And that'll be it. This can't be written in y equals mx plus b form, so we'll leave it. That's all. All right, numbers 7 and 8 say find the domain and range, determine whether it's continuous or discrete, and explain, or discrete or continuous and explain. So on number 7, what we have is a continuous function there. It's continuous because all the points are connected. You can't, if you don't lift the pencil from the paper to make the drawing. That's kind of the way that I describe that one. Continuous, all the points are connected. I'm not very good at getting explanations on those. Explanations that make sense to you, sure. One that makes sense to a mathematician, probably to a mathematician. To a mathematician, to a way that I can answer it for you? That's the part. All right, here's the domain and range aspect. Let me copy this graph over because I need us to understand something, because a lot of times we won't. This graph has some weird stuff going. And if you guys, if IM3 students will probably know what this is. This is called a cubic function. But here's the thing. Does this graph go up and down forever? I think we can all agree yes. The arrows tell us so, right? So when they say domain and range, for range we can say it's all real numbers. Here's my symbol. Domain's a little different story. Does it go left and right forever? Here's left, here's right. People will say no. What? But wait a second. The arrow says it goes forever. Yeah, because it goes forever down. Wait a second. Are you telling me that it goes forever down, like straight down, that it curves back? What do you mean? No, it goes a little down and it goes a little left. Well, how far left does it go? I don't know, to -2? No, it keeps going left. It might go down sharper than it goes down left. It might go up sharper than it goes right. But it goes left forever, it goes right forever. This is a function for which you can say, this is actually the graph probably y equals x cubed, like I said, a cubic function. And there's no restriction on x. I can substitute any x value in the world that I want. I will get a y value, which will be significantly taller than those x values. These domain and ranges are all real numbers. You can say it goes from -infinity to +infinity on x, from -infinity to +infinity on y, and that's what this one is here. And it's continuous. It hits every point in between and then some that way. So that's my over explanation on number 7. Now, number 8 is a discrete relation here. Number 8 is a discrete relation because your points are disconnected. There's a finite amount. They are very specific points. So number 8, discrete. The points are disconnected And I guess I'll say finite in the way that when we write this out for domain and range, we get to write a list of numbers. It's specifically this x value and this x value and this, etc. Now, the tricky part about number 8, which I guess I should copy and paste, is this graph is scaled by 2's because I see a 4 that's 2 over, and I see, like this. So these are scaled by 2's. So when you see these values here that look like they're at half marks, that actually is 1. This is 1, 2, 3, 4, etc. So just be careful when it comes to that. Now, domain is your list of x values that exist on your graph. The furthest left x value we get is right here at x equals, remember, that's -2. And then it hits -1, and then 0, and then 1, and then 2, and then 3. It goes from -2 to 3, but it's discrete, so it only hits those specific values as a list. Write them in increasing order, no duplicates, which of course they don't have any. The range we'll list from bottom to top. Same kind of format, but we have to figure out what those y values are. The lowest y value is -8. And then it look, it's linear, so it has this increase in jump. It goes up 3, it looks like. So it goes up to -5, and then -2, because they're going by 2's, and then 1, and then 4, and then 7. So there's domain and range. Now, this isn't a mapping diagram, but 3 actually points to -8, and -2 points to 7, etc. Even though they're written in this different order, they're just not maps to each other. That's what a mapping diagram's for. This is not that. So it's discrete. There's our domain and range. Discrete has lists. We're all done. Number 9 says evaluate h of x equals 12 minus 5.2x when x is -4, 0, and 3.5. We might have to use our calculator. So h of x equals 12 minus 5.2x. We have to come up with h of -4. h of -4 is 12 minus 5.2 times -4, which is 12 plus, I think, 20.8, which is 32.8. So here's h of -4. When x is -4, y is 32.8. Weird number. Hopefully I calculated that right. H of 0 should be an easy calculation. This term actually goes away, and you're just left with 12, right? 5.2 times 0 is 0. So 12. And then h of 3.5, we have to do 12 minus 5.2 times 3.5. Just so I don't mess this up, I am going to use the calculator, and I'm going to do the entire thing. 5.2. Oh, this is not typing anything. Of course, my calculator is going to do that. Give me 1 second. 12 minus 5.2 times 3.5. And I'm getting -6.2 as a whole. That's the final result. It must have been -18.2, -18.2, I think, as a value. Is that right? 5.2 times 3.5? 3.5 times 5.2. Yeah, it's 18.2. Huh, interesting. Okay, so that's number 9. That's evaluating those ones. Number 10 says for g of x equals 3/4 x plus 7, find the value of x for which g of x equals -2. This time we're substituting for y, not for x. So we have the equation here. We need to do it for g of x equals -2. G of x just means y. So y equals -2. There's our substitution. Let's solve for x. I want to subtract 7 from both sides to get the x term by itself. It is a 3/4. I would love to multiply both sides by 4/3 to counter that and solve for x officially. Now, -9 times 4/3 is -9 divided by 3 is -3 times 4 is -12. X equals -12. That's what we would have to input into this equation to get -2 for y. Number 11 says find the slope and y-intercept of the graph of this one here. Now, this is neither in standard form nor slope-intercept form, but it sounds like this time we'd really want to do a little more slope-intercept form work for this equation. If we can get y by itself, then our y equals mx plus b will tell us what the slope is and what the y-intercept is. So let's get this 4y by itself. Let's subtract 3 from both sides. Now, I'm going to write the 4y on this side of the equation. Hope you don't mind there. I got a -x. I got a -3, which did not combine. If I divide these by 4, y will get by itself. And a little tricky bit here. I'm glad I'm not graphing this one. Not because of this fraction, because of that fraction. But this is indeed a fraction. -1/4 is multiplying by x. This is your m. Your b that's adding to that term is negative 3/4. So here's the equation. Our slope of this is negative 1/4. Our y-intercept, very uncommon for us to see this, is negative 3/4, which means the point that it crosses is 0, negative 3/4. That's not a point that we generally like to graph like that, but we're not graphing it. So that's kind of nice. But putting it in the form gets us those values. Now we also could have found the y-intercept by setting x equal to 0 and solving, but I think the slope was best resolved this way, so we were best doing it that way too. So there's your answer set. Okay, numbers 12 and 13 say graph f and g. This is where I said we will graph out a slope-intercept form. Describe the transformations from the graph of f to the graph of g. This would be out of section 3.6. There are some folks who maybe wouldn't have done section 3.6, so move on along, if so, to some other questions, because I'm going to go straight into this one. F of x equals x, that's your parent function, and g of x equals negative x plus 3. If I were to graph these as they are, f of x equals x is actually going to appear in the next two problems. So let's graph this one right now, and let's get a next graph ready for this as well. This is f of x equals 1x plus 0, a slope of up 1/1 with the y-intercept of 0 like this. If I plot as many points as I can fit, I would go up and down like this right here. I'll change that to black. I'll fit that a little more closely, and then we'll get that ready to go because we're about to do another graph with this. Now, there are a lot of ways which you can answer this because they don't tell you how you must, I don't know how I say this, they don't tell you how you must apply your transformations or describe them. Do you graph this first and then describe it? Do you use this equation to describe it? I don't know. But negative x plus 3 is a y-intercept of 3, and it's down 1, right 1 like this. So this has a flipped over appearance as well. But with this slope, yeah, so this slope's negative 1. But yeah, let's start describing the transformations. Let's do it maybe based off the equation. The equation shows that a negative 1 got multiplied by this x that we had before, right? Before we had a slope of 1, now it's negative 1. That means the graph of g is a reflection in the x-axis. From f, followed by, we add 3 up, right? Followed by a translation 3 units up. So those are the two things that got applied in this function here. G of x is taking your f of x equation. Let me write this right here. G of x takes your f of x equation. It flips it over its y values. It flips over the y's, and then it adds 3 to all your y values like that. And that's what we're doing on ours. Number 13 does some more of the verticality things. Let's see. So number 13, same parent function. G of x is 1/2 x minus 5. So we can make some of the same statements as we had before. Now I can use this same parent, whoops, it didn't copy, of course. I can use this same parent function right here. Now we say 1/2 x minus 5. For the sake of practice, let's kind of go the other way on this. Let's say g of x equals, so what happens to x? It got multiplied by 1/2. Our function just got halved, and 5 is being subtracted from it. So what do we do to our function? We vertically compress it. The graph of g, or vertically shrink it, is a vertical compression by a factor of 1/2, followed by a translation 5 units down. So these ones seem to avoid doing any horizontal things. These ones didn't have any other reflections, but no horizontal translations, things like that. We'll just leave it as it is. But let's graph this one at a slope-intercept form so we can practice it. Y-intercept of -5, and we're going up 1 and right 2. So that 1/2 fraction, up 1, right 2, like so. This is the graph. So there is a way of taking that black graph, vertically compressing it, so it's half the size. Instead of up 2, right 2, it's up 1, right 2. And then we moved it 5 units down. That's why this graph is as low as it is, and as less steep as it is. A shallow slope, if you will. Okay, number 14. Function A represents the amount of money in a jar based on the number of quarters in the jar. Function B represents your distance from home over time. Compare the domains. What? I have no idea what they're talking about. Function A represents... Oh, okay. I thought they were talking about, like, make equations, things like that. I'm like, they didn't give us anything. I thought I was missing information. They're just saying... Function A is the amount of money in a jar based on number of quarters. Based on the number of quarters. When it says compare the domains, my domain for function A, the domain is number of quarters. Well, first of all, the independent variable is number of quarters. Its domain would be discrete. Domain is discrete because number of quarters needs to be integer, whole number values. Whole number of quarters. For function B, it says your distance from home over time. Your independent variable is time. This time. Time could be minutes, seconds, hours, weeks, whatever, how far you are from home. Are you vacationing? Are you riding your bike? Are you walking? Being escorted home by an Uber? Things like that. So that's time. Time is normally continuous because you can measure home within any amounts of things. Even if it's minutes, you can be home within a fraction of a minute. So your domain here is continuous because time can be represented fractionally. I'll say fractional. So when they say compare the domains, I assume they mean this is discrete versus this is continuous. I can't think of what else we would talk about there. Oh, regarding the domains themselves, the domain here I could represent from like 0 quarters and onward, 1, 2, etc. I don't know how far that thing goes. For time here, your times domain can be some sort of time that's greater than or equal to 0. In that sort of way, that can state to infinity as well, but we would write that as an inequality. The other would be a list. Number 15, a mountain climber is scaling a 500-foot cliff. The graph shows the elevation of the climber over time. So hopefully you can see that little itty-bitty graph. If you can't, let me bring it up. You can, of course, download the PDF and you can see it there. I think that's a clear enough. It's not clear, but that's a clear enough probably picture of what we have to do. So number 15, there it is. Part A, find and interpret the slope and the y-intercept of the graph. Okay, I probably didn't give myself enough room to do that. So let me just move this over, scroll this down, things like that. All right, so number 15, boom, part A, the slope is, it's this number here, 125. So this is how many feet and time in hours. If my slope's 125, that's also 125 over 1. Slopes are rates. That's 125 feet per hour. Slope is the mountain climber is ascending at a rate of 125 feet per hour. The y-intercept states where the mountain climber was when we started kind of tracking time in hours or whatever. The mountain climber began at an elevation of, and if you can't tell where it's crossing the y-axis there, that's what this number here is for on 50 feet. Maybe that's 50 feet above sea level, whatever else. Maybe you started on a 50-foot plateau. But that's where, maybe that's when we just started measuring time. Like, okay, ready, go. But it's at 50 feet. Part B, explain 2 ways to find f of 3, then find f of 3 and interpret its meaning. Well, one way we can find f of 3 is based off the equation. So we can say f of 3 equals, and we substitute 3 for x in that equation, 125 times 3 plus 50, which is 375 plus 50, which is 425. In terms of interpreting its meaning, we're going to get to that after the other one. The other way we can do it is off the graph. Now 3, this one's going to be kind of tricky because 3 is not right on these numbers. Not only, oh my goodness, what? Oh my goodness. So this is like 0.4, 0.8, this is 2.8. 3 is probably about right here. When x is 3, what is your y value? That's what we're looking up, and that's going to be this point right here. So this is the point 3, 425. That's a second way to find it. Will you find it exactly? Probably not as well. So if they ask which would you prefer, when I have the equation, I'd prefer that, but this is the representation as well. When x, time in hours, is 325, your elevation 3 is 425 feet. So what they're stating on f of 3 is 3 hours into the climb. After 3 hours, the mountain climber's elevation is 425 feet. Okay. Part C. How long does it take the climber to reach the top of the cliff? Justify your answer. They said the top of the cliff. Oh, I thought it was a mountain. Oh, because mountain climber. The cliff is 500 feet. So we have to figure out for what value of x we get an f of x of 500. So I'm going to, or it's right here. So we have two different ways to do this one. If I have an option, I might, if I have an option here, I might take the graph version. I'm sorry, I'm trying to move this point. It's my program's really weird as far as when things group together and when they don't. So I have to do some movement on this. So they're actually showing the top right here at 500 feet, and the time is right here. And if you can understand these scales, between 3.2 and 4.0 is 3.6. So I believe it's after 3.6 hours, or 3 hours, 36 minutes, if I'm going to be really technical. After 3.6 hours, that should work. So I believe it's going to be x equals 3.6 hours. Let's see if that is by going into our equation, because we can also do it this way. We can substitute 500 into our equation, 125x plus 50, and solve for x. We subtract 50 from both sides, and then we divide both sides by 125. Now, let's go to the calculator and see what that ends up being. In the calculator, we get 450 divided by 125, and we get 3.6. So that was exactly what we expected there. So x equals 3.6. So it'll take the mountain climber 3.6 hours to reach the top of the 500-foot cliff. All right, there it is. Whoa, I wanted to box that. Okay, last one on the chapter test, number 16. Without graphing, compare the slopes and the intercepts of the graphs of the functions f of x equals x plus 1 and g of x equals f of 2x. All right, so number 16, they said without graphing, so we won't. F of x equals x plus 1 and g of x equals f of 2x. What I can actually do here is I can substitute 2x in for x in this equation, and that'll say g of x equals 2x plus 1. I know it's a little particular for me to write the 2x in parentheses, but it's a reminder of if something was in front of the x, like a 3, then the 3 is still out there, and I don't want you to lose that. Anyway, this is just 2x plus 1. So this one versus this one, the slope, compare the slopes and intercepts. The slope is 2 versus 1, so twice as big. I don't know. Vertical stretch by a factor of 2. So the slope is 2 over 1. Shoot. I don't know how I want to write this best. Give me a second. Turn this in black. So this one has a slope of 2 over 1 and a y-intercept at 0, 1. This one had a slope of just 1 over 1 and a y-intercept of 0, 1. So the vertical stretch factor is 2. The y-intercepts are the same. You know what, though? It's not just a vertical stretch by a factor of 2. That's how we think of slopes on the outside. But this was also, or a horizontal compression by a factor of 1/2, which I don't know how much they want to talk about that specifically, but that's what's happening. When you see a 2 inside of here, it's actually horizontally shrunk, which also makes vertically stretched. It shrinks by the same amount that it stretches whenever it's a linear function like this, and that's what this one is. So we didn't graph. I'm not graphing. I'm moving on. So guys, that's going to be the chapter test portion. We're going to move on now to the cumulative assessment, which has 10 questions on it on whatever it's going to be from chapters 1, 2, and 3. I haven't seen them yet, and so I'm going to be as caught by surprise as you are. Let's take a drink, and let's go for it. Okay. Always interesting, these are. Number 1, you claim, well, this looks weird. You can create a table, he can create a table of values. This looks really weird to read. All right, you claim you can create a table of values that represents a linear function. Your friend claims he can create a table of values that represents a nonlinear function. Using the given numbers, what values can you use for x and y to support your claim? What values can your friend use? Why don't I bring my friend over and we can find out, right? Let's looks like values will have to repeat themselves every so often, so get ready for that. I'm going to bring in my claim and my friend's claim. I need to create a linear function. In order to do so, my x's must increase by a constant amount. So do I have options to do that in any sort of way? Yes, I do. I can say do 1, 2, 3, 4 for x. There's no problem. And I probably want to do the same thing for the friends just to be sure that all's good. As long as 1, 2, 3, 4 are there, I'm good on that. Now for myself, and I don't want to get too... You can create a table of values that represents a linear function. Using the given numbers, what can you use for x, y to support? Oh, am I allowed to repeat though? Here's my guess. I'm guessing I'm not allowed to repeat my own values for x, if that makes sense. So I'd rather use negatives and not make that mess up. So I'll say -4, -3, -2, -1. They still increase by ones. I want to not repeat my own values in my own claim. So now I want to use these other numbers here. So for this one, I can use say 1, 2, 3, and 4. And if I do, then they all increase by a constant amount. For the friend, I can do the same thing, like -4, -3, -2, -1. But make sure they don't increase by a constant amount. And I can honestly make something up. I could say 0, 2, 3, 5. And that would be good. 0, 2, 3, 5. So we can do that. Kind of interesting. Basically, we need these to go by constant amounts. They don't have to go by ones. And I could have gone pretty tricky if I wanted to, but I wanted to make sure something worked. Number 2, a car rental company charges an initial fee of $42 and a daily fee of $12. Use the symbols and numbers to write a function that represents the situation. Strangely enough, actually, I don't know what chapter this is technically from, but strangely enough, out of chapter 3, they always wrote the equations for us. We never got to write ones for ourselves. So if this is chapter 3, this is a first. It charges an initial fee of $42 and a daily fee of $12. Because it says function, I'm guessing we're going to be talking about chapter 3. So f of x equals, you really want to think slope-intercept form. Daily fee is like your rate for every day. That's like a slope. So 12 times the number of days plus the initial fee of 42. That means even on day 0 up front, you're paying 42. Here's a function, part A. Oh, I totally didn't even see this information here. So f of x equals, perfect, 12x plus 42. There you go. I didn't even see that. Part B. The bill is $138. How many days did you rent the car? This is where f of x represents $138. I guess that's where the 138 comes from. We shouldn't know that information yet. But now I guess we do, right? Now we use it. So we're now going to say an equation, 138 equals 12x plus 42. And we subtract 42 from both sides. And we get 96. And we divide both sides by 12. And that's 8. Whoops. And that's x equals 8 days of rental, of car rental. So we rented it for 8 days. That's what would total $138. Pretty cheap, I think. Is that upfront cost, man? Number 3, fill in the values for a and b so that each statement is true for the inequality ax minus b is greater than 0. This is clearly out of chapter 2. So ax minus b is greater than 0. Let's see. They're showing things as far as solving for x goes. The thing I'm going to do on both sides to start with is add b. And then I'm going to divide both sides by a. I have ax is greater than b. And then when you divide both sides by a, one of two things can happen. X can either stay as greater than b over a, or x can be less than b over a. I'm not saying both are allowed. I'm saying one of two will happen based on what they're going to talk about here. This is what they mean. Part A says when a equals this and b equals this, x is b over a. It says fill in values. So I get to choose my own. So when a equals and b equals, whoops, and b equals this, then x is greater than b over a. What would keep this as greater than in this case? To stay as greater than, a would have to be a positive number. Now, a is not allowed to be 0, period, on this because you can't divide by 0. A would have to be a positive number, so make one up, 3. Tell you what, b could be anything. B could be anything, and you're adding that number over. So if I said that B was, 5, that means at the time this actually said 3x minus 5 is greater than 0, and then I add it over, it turns positive. Even if it was negative, that's fine. It still flips it over. So that would give it, so 3 and 5, that works. Now for the next one, for B, when A equals blank and B equals blank, X is less than B over A. What would make this thing less than? Dividing by a negative. And again, it doesn't matter. It doesn't matter what B is. B can still be 5. I can make it 7. It can be positive. It can be negative. B can be 0. A is not allowed to be 0, but this time A would have to be negative so that dividing by it would flip it. So A has to be something else. Let's say negative 1. If A is negative 1, then we have 7 over negative 1, and it flips the inequality. So that's what makes that happen when you solve. Number 4. Fill in the inequality with less than or equal to, greater than or equal to, so the solution of the inequality is represented by the graph. Okay, so we have a graph on number 4. I'll kind of draw my own version of it. Haven't done these in a chapter. 1 is my boundary point. There's a closed circle on it that goes here to the right. Our variable here is an x. We need this to eventually say x is greater than or equal to 1. That doesn't mean this inequality will state greater than or equal to. Let's see. Negative 3 times x plus 7. Now I do this temporarily. I'm going to put an equal sign here temporarily. It's not going to be. It's going to be an inequality. We'll state if it flipped what, we'll change it. We'll change it later. Listen, I can, actually, let's do this. I'm going to divide by negative 3 straight up. Dividing by negative 3 will reveal and resolve exactly what we need. Eventually, I need x to be greater than or equal to. So that means when I divided by the negative, that's when it flipped, which means this would have been a less than or equal to. So here's going to be the answer. It will be less than or equal to originally, because now you subtract 7. Now it'll say x is greater than or equal to 1, which is what this graph is, which is what that is on the number line. That means, though, originally it was this, but dividing by the negative flipped it. So there's your answer, less than or equal to. Number 5. Use the numbers to fill in, these chapter tests are so weird, or cumulative assessments. Use the numbers to fill in the coefficients of ax plus by equals 40, so that when you graph the function, the x-intercept is negative 10 and the y-intercept is 8. Well, this goes back to chapter 3. The x-intercept is going to be when you set y equal to 0, so it's ax equals 40, divide both sides by a, and x equals 40 over a. If x equals 40 over a, our 40 over a needs to equal 40 over a needs to equal an x-intercept of negative 10. So 40 divided by what number gives you negative 10? Negative 4. 40 divided by negative 4 is negative 10, so this should be the a value there. The b value is by finding the y-intercept by setting x equal to 0, by equals 40. We divide both sides by b to get the y value. This will be y equals 40 over b, not y equals. 40 over b equals, where's the y-intercept? 8. 40 over b equals 8. So 40 divided by what number is 8? That number is 5. So b would have to equal 5. And there is that number there. So the numbers exist. So our equation, they said fill in the coefficients. Therefore, our equation will say negative 4x plus 5y equals 40. That would give us those two intercepts. Okay, number 6, solve each equation, then classify each equation based on the solution. Explain your reasoning. I guess by classify, is it one solution, no solution, infinite number of solutions for these? This will be a chapter 1 thing. I'm going to do these equations pretty quickly. These have been here for a while now, or what we've been doing with them. Subtract 2 x's to keep them positive, add 33's to move them over to the other side. 33 minus 9 is 24. And this is 3x. Divide both sides by 3. Get x equals 8. So that's one solution. I don't really have an explanation for it. I could get x by itself. Therefore, I have one solution. Honestly, guys, I'm not going to do the explanations. I'll state them out loud for you. You get one answer. There's one solution. Part B. 5x minus 6 equals 10x plus 10. Once again, I'm going to make my x terms positive personally. I'm going to go for it. So subtract 10 over here. I have negative 16 here and 5x over here. Kind of a weird looking answer we'll get. We'll divide by 5. We get x equals X equals negative 16 over 5. That's negative 3.2. That's good. Still one solution. Is that what they mean by classify the solution, though? But anyway, it's the only one. To explain the one solution thing, guys, this is the only value for x that's going to make this equation true. Right? That's what the one solution means. It's not just this is why it's one solution, but that's what one solution represents. Now, we're going to get some other situations here. Let's see if this is one of them. 2 times 8x minus 3 equals 4 times 4x plus 7. Otherwise, if everything's one solution, that'll be kind of awkward. Let's distribute these values here. That's 16x minus 6 and 16x plus 28. If I subtract 16x from both sides, they go away. And we get now an equation set that says negative 6 equals 28. Kind of an Nothing's wrong. It's just there's no x that'll be right. There's no solution to this thing. My explanation is no matter what x I substitute into here, the left side will never equal the right side. That's our no solution cases. They become inconsistent with our set. Okay, I'll distribute the 2 into these two. Not the same coefficients for the x terms on both sides here. That's negative 20.2. So there will be solutions. Once again, I'm putting variables on the right side if I want to keep them positive. That's your call. But here it makes everything positive. I think we'd prefer that personally. 25.2 equals 9x, and we divide both sides by 9. I don't know. Let's see how clean that number looks to begin with. Oh, it's clean. It's 2.8. It's a decimal, but it's 2.8. So x equals 2.8, and that is one solution. Once again, 2.8 is the only number that will work out in that situation, apparently. That's part D. Part E. Same set. 6 times 2x plus 4 equals 4 times 4x plus 10. If we distribute here, then we get 12x plus 24 equals 16x plus 40. I'll be honest, I expect, well, first of all, it's weird that every single time I got to move the variable terms to the right in order to get them positive. I figured at least once would make it the other way. Secondly, I'm surprised there's so many one solution cases here. I thought we were going to get a bunch of no solutions, infinite number solutions. I'm guessing the last one has to be infinite number solutions because, man, this is just one solution left and right. I guess we still got to practice solving, I suppose, but also one solution there. Now, the last one, F. Part F, we say 8 times 3x plus 4 equals 2 times 12x plus 16. 8 distributes into both of these. 2 distributes into both of these. We get 24x plus 32 equals, here it is, 24x plus 32. We subtract 24x from both sides. We get 32. Oh, I said 32, but I wrote 36. 32 equals 32 is what shows up here, which I guess is a true statement. It's a way of stating no matter what x happens to be here, we get an infinite number of solutions. Infinitely many solutions. Now, I'll be honest. We've been stating infinitely many solutions all these times here. I used to put, I'm not sure if I'm right or wrong on this, I used to put all real numbers. I mean, I'm not wrong. All real numbers works. Infinitely many solutions is true as the set of them, or as the amount of them, but the set of them is all real numbers. And I really want to start putting that and really start differentiating that. But the idea is I can plug in any value for x, and the left side will always equal the right side in that case. Okay, 4 more questions. Number 7. The table shows the cost of bologna at a deli. Plot the points represented by the table in a coordinate plane. Decide whether you should connect the points with a line. Explain your reasoning. Now, I don't know if they're asking for you to determine whether it's a linear or determine whether it's continuous, right? I don't know if that's what they're asking because I don't know if it's linear or not. Actually, as we look at it, it does look linear. When I look at these points here, and this is where I feel like I kind of want to change scale, you know? I don't want to make this so slim. I'm going to change my, I think my y values can stay as they are. The 12 ain't so high up that it's unreasonable to fit. The x values would be so slim if I leave them as they are, though. So let's kind of change those up a little bit. Let's go, x's will go by 1s like this. 1, 2, 3. Actually, even more so. Let's do this. Let's really widen this out. 0.5, 1, ignore that, 1.5, and 2. So every 2 is another 0.5 on there. And then we can really fit these here. At 0.5, we have $3, 0.5 pounds. At 1 pound, we have $6. At 1.5 pounds, we have $9. And at 2 pounds, we have $10, $11, $12, like that. So are they linear? Yes. Should we connect them with a line? Depends on what they mean with the word line. Technically, when we learn the word line for geometrics, it means it goes both left and right forever with arrows. I think they just mean that should we connect it? I think we should, because our x is represented in terms of pounds, and even though it's $3 for half a pound, what if you have a quarter of a pound? Should we pay $1.50? I think so. I think that we can sell them. We don't have to either take half the pound or not. I think these are just increments of what we have here. So my idea of a line for this one is technically called array, that we start from the origin here. We don't spend any money, it was no poundage. So I guess the 12 is a little higher up. I might have just missed the mark. So about right there. So do we connect with a line? Yeah, I think so. That you can pay fractional amounts of meat. We connect with a line because we can pay for fractional amounts of meat. Of bologna. Okay. Number 8. The graph of G is a horizontal translation right, then a vertical stretch, then a vertical translation down of the graph of f of x equals x. Use the numbers and symbols to create G. Oh my goodness. And now, we can choose our own G here, but we have to use these numbers within somewhere. To create G, here's f of x equals x. G of x is some version of f of x, okay? So G of x takes your f of x equation and does the following. Horizontal translation to the right. That means we have to subtract something within here. To go right, we go opposite of. Now, I don't know if the formula itself shows the minus, therefore I'm technically choosing a -1 or a +1 here because it shows a minus in the formula. We can, either way, we can put a 1. Maybe that's why they're putting both so you don't confuse yourself. It says, and then there's a vertical stretch, which multiplies by your function outside of there. So I can do something like this. Let's vertical stretch. We don't reflect. So to stretch it, we got to use, say, the 3. I think I have to use the 3 for this one. What else? Then vertical translation down. Because I might have already used the -1 here, I can either use the -3 or the -1/2. Either or. I'm going to use the -1/2 just to be different there. So -1/2, that is a translation down. So if that's the function there, our function is x. We turn that into 3 times, instead of x, it's x minus 1, and then -1/2. You know what, the -1/2 looks way too weird because I actually want to combine like terms. What was the number I didn't use? I didn't use -3. So let's say -3, and that's -3. Here's a version of the equation. Of course, if you wanted full slope-intercept form, you would distribute like this, and it would be 3x minus 6. But because we need our answer to look like one of these other ones, I'm going to have to keep it, I think, like that. But that's what you can do with it in order to get the final bit. So there is what I'm going to write as the equation. We used this. I think. We use this. We use this. We use this. And -1, -3. And we use this. And this. And this. Okay. Something like that. All right. Oh, and parentheses and all that kind of stuff. Okay, number 9. What is the sum of the integer solutions of the compound inequality? Oh, the sum. This is kind of like an SAT question thing where you can't just plug in answers. You got to find the answers and then add your answers together. Now, if you add negatives together, or a positive with a negative, it becomes subtraction. I'm going to divide both sides by 2 in this set, get the absolute value, portion by itself in the inequality. We must stay within 8 units left to right of 0. So we must stay less than the positive 8, and we must stay greater than the negative 8. Whoops. X minus 5, or yeah, greater than negative 8. Add 5 to both sides, and we will have an x that's less than 13, and add 5 to both sides. Here we'll have an x that's greater than negative 3. So our inequality set goes from negative 3 to 13. If you graphed on a number line, I don't know if we have to, but if you graphed on a number line, it would look like x's are between these two guys right here. They said, what is the sum of the integer solutions of the compound inequality? I don't understand that because there are, what? What is the sum of the integer solutions of the compound inequality? I'm between 13 and negative 3. What do they want? I don't know what they want. Hold on, let me pause and think about this. Okay, I realized what they wanted immediately after. I'm sorry about this. I thought they just wanted two numbers to add together. I'm like, there are no two numbers between here I could add together to get that. Now I get it. We got to add all the numbers in between here that work. So, between negative 3 and 13, include the numbers. Negative 2, the integers. Negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, there are ways to do this more quickly that you wouldn't know for another couple years when you do arithmetic series. I do happen to know that adding 1 with 10 together gets you 55, so the 0 is a part of that. So these are 55. This is something I've done a lot before. 11 plus 12 is 23, and negative 2 minus 1 is negative 3. So all these together, negative 3 plus 23 is 20. So 55 plus 20 is 75. And 75 is option B. Okay. I was so confused. For some reason, I was just thinking of two solutions. I'm like, did they really want us to add negative 13 or 13 and negative 3, and those are not solutions? Did they want us to pick any two solutions? Those don't add together. Did they mean add the digits together? And then I totally realized, oh, they literally want all the integers in between. Okay, so sorry about that. All right, last question is number 10. Oh, the struggle's real. Your bank offers a text alert service that notifies you when your checking account balance drops below a specific amount. You set it up so you're notified when the balance drops below $700. The balance is currently $3,000. You only use your account for paying your rent. No other deposits or deductions occur. Your rent each month is $625. Part A says write an inequality that represents the number of months M you can pay your rent without receiving a full text alert. We need our full text alert to stay above $700. Or at $700. It says only when it drops below do you get an alert. So we have to stay greater than or equal to this. We have $3,000 in balance, and we deduce $625 every month for M months. Here's our setup. This is the money that needs to stay above or equal to $700. Part B, what's the maximum number of months you can pay your rent without receiving a text alert? So in terms of solving this here, I'm going to keep this on this side. I'll subtract 3,000 from both sides. And we'll have negative 625M is greater than or equal to negative 2,300. We'll divide both sides by negative 625. Is that an even amount exactly? This is 1250 doubled. No, I don't think that's an exact amount. So let's do 2300 divided by 625. That's 3.68. So M, now this is going to be less than or equal to. The inequality flips when I divide by a negative, so 3.68 months. That means after 3.68 months, that includes month number 4, text alert. So we can only get to 3 months before text alerts happen. On the 4th, text alert. Part C, suppose you start paying rent in June. Select all the months you can pay your rent without making a deposit. So if I start in June, then I get the next 3 months afterward, right? I get June. This is kind of like a domain. My domain is June. And then I get, I believe, July, August, and September, because June is where I still have the $3,000. After July, I lose $625. After August, I lose another $625. After September, I lose another $625. Then I still have a few dollars left, few nickels to rub together. But on October is where I have that other deduction that I'm having a problem. So June is all good at 3,000, right? It's kind of like domain and range. June, July, you'll lose what? Now you're at 2375. August, you're at 1750. September. Wait a second. Did I say that right? Maybe June is where you have the deduction. Hold on a second. Let me think about this now. Losing 625 a month. So maybe this isn't the 3,000. Maybe you already have the deduction. So here you have 2350. Sorry, 2375 and then 1750. 2375 and then 1750 and then 1125. I have to make sure I'm doing these numbers right. And then 500. And then in October, it rings up. Okay. Now, it's still 3 months because of how we solved that, but that goes in the way of June being the first month with deduction. Oh, because that's us paying rent, right? This isn't just deduction from bank account. This is us paying rent for the month. Totally making sense. We start paying rent in June. Okay. So, yeah, that's it. Up to September. All good to go. All right, guys. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching the Chapter 3 test in cumulative assessment. We'll get going to Chapter 4 next, and I hope that you do well in whatever tests you have coming up. Thank you so much. Take care. I'll see you in the next one.